Hello guys, welcome again to our lecture. So we're going to continue talking about chapter 5, and the last part of chapter 5 is about arithmetic operations, basically the add and the subtract instructions. So we're going to do, or we're going to explain or demonstrate the add and subtract instructions with unsigned numbers. So it will be unsigned addition and subtraction. So unsigned numbers are the data in which all the bits represent the information, or represent the number, and there is no sign bit. So if you have 8 bits, the complete 8 bits represent the number. If you want to convert these 8 bits to their decimal equivalent, you should use all the 8 bits. If it's a signed number, then the 8 bit number 7 or the 8th bit represents the sign. But this is not the case with unsigned numbers. If you have 8 bit and you're going to use all bits for the to represent the number, then you can represent the numbers from 00 until FF, or in decimal equivalent 0 to 255 as a max. And for 8 bits, or 16 bits, you can represent the numbers from 0000, of course hexadecimal, until FFFF hexa, which is 0 to around 65,000 as decimal. Okay, and as we said, we're gonna illustrate or demonstrate the add and subtract instructions with these numbers, unsigned numbers. So let's start by the add instruction or the addition. Here is the general format for the add instruction. You have add, the instruction or the mnemonic itself, destination and source. This is equivalent to this. So we are saying here destination equal to destination plus source. Okay, destination equal to destination plus source. There is also another add instruction which is add if carry. Okay, and we're gonna explore this in our examples. Add if carry means add or make the addition if the carry bit is 1. Okay, so let's talk about the destination and source operand. So the destination operand in the beginning, can be a register or a memory. So you can, for example, say add AX BX, or add, like 40 and BX. So here the destination operand is a register. Here the destination is, a memory location. So go to the memory location number 40 and put the result there, or add BX and the value in that location and put the result, or update, the memory location 40 with the addition result. The source operand by itself can be a register, memory, or immediate. So you can say add again AX and BX. Here the source is a register. You can say add AX and 40. Here the source is is a memory location number 40, or you can say add AX and 40. In that case here 40 is not a memory location, 40 is a number. So you're gonna add, so this is equivalent to AX equal to AX plus 40. So add 40 to what's inside AX register and update, or update the register AX with the result of the addition. One note here that we should consider is that memory to memory operation is not allowed. So you can't say, for example, add 40 and, for example, 20. You can't say so. That's wrong. You can't add directly two memory locations together. And of course, both add and add if carry instructions will update or would change, for example, the flag register. Exactly, the 0 flag, the sign flag, the auxiliary carry flag, the carry flag, and the parity flag. Okay. Let's see an example of addition of individual byte or word data. Okay, so you have here, array. We say this is an array. You have 5 locations in that array. These numbers are less than 255. Remember, 255 is 8 bits. 255 in specific is 8 ones like this. 8 ones in decimal is 255. And all these numbers are less than 255. So all this number can be represented by just 1 byte. Okay. So in that example here, we're gonna add all these numbers together. But the problem is when you add, for example, 125 and 235, the result here, which is let's do this, 360. This is more than 8 bits, because this number is greater than 255, and 255 is 8 bits. So 360 is for sure needs more than 8 bits. That's why the variable in which we're gonna store the the final result is word. Okay, some here is word. So we do this addition example similar, but with a slight difference to what we have done before in our labs. Okay, and we're gonna see more in the lab, in our labs about this this example here. But I'm gonna do it with you guys. So here, first we define a constant, which is 5, because we have here 5 numbers, and we're gonna use AX, and the X, remember, is a 16-bit, is 8-bit, is 16-bit. But we're gonna accumulate the result in AL first, and in case there is a carry, we're gonna move this carry to AH or increase AH. So of course one may say we can use AX directly because it's it's a word, it's 16-bit, and it will so save us time and save us basically code. But this was an example in the book, so I'm gonna explain it to you because it's interesting. So here it uses AL, which is 8 bits. Although some of the result might exceed 8 bits. Like for example, if you add 125 to 235, this will exceed 8 bits. We're gonna need for this one in specific 9 bits. Okay, so what we're gonna do is that whenever we have a carry, we're gonna increment AH. So let's do this step by step. So let's first add 125 with and 235. Okay, this addition will be like this. If you add these together, this will give you the following result. I already did it, so we don't need to waste some time here. So this is 9 bits. This is 9 bits. And as you see, 8 bits, and this is the 9th. Okay, so in that case, we should use we should use AH and AL together, or AX. Okay, we should use both at the same time. So what we're gonna do, we're gonna save this number here, which is 100 and 0110, or 68 as hexadecimal in AL. And we're gonna put this one in AH. Okay, that's why we say here after adding AL and what's inside is a memory. So in the beginning, in the first iteration, we're gonna add 125 and 235. Okay, and we said that here jump not carry to over. If there is no carry, go to over, but if there is a carry, increment H. Of course, in the first iteration, we're gonna have a carry, so H will be incremented and the H will have 1. And the L will have this number here, 68 hexadecimal. Then we go forward and add to this number 0, 1, 1, 0, 1, 0, 0, 0, which is the result from the first iteration, 197, which is again 8 bits. So this will be 0, 0, 1, 0, 1, 1, 0, 1. If you make the addition here, this should be 1, 1, 0, 0, and 0, 1, 0, 1. This will give you 1, 0, 1, 1, 0, 1, 0, 0, and again there will be a carry. Okay. So what's gonna happen here? Again, this will go to AL, and the carry will be added to what's inside the H. So H will be 2. Okay. So, or 0, 1, 2 in binary will be 0, 1. So again, after adding the 197, there will be a carry, so this will not be executed, and we're gonna increment H again. Then you add the 91, so you take 0, 1, 0, 0, 1, 0, and 1, 0, and 1, 1, 0, 1, and you add to it, the 91, which is 1, 1, 0, 1 here, and 1, 0, 1, 0. If you add this will be 1, 0, 0, 0 here, and 1, 0, 0, 0. And the carry is 0. So in that case, we don't need to increment H. AL was enough for us. So AL will take this, and we will not increment H. So in that case, since the carry is 0, we're gonna go to over. Okay, and just increment each side so that we point to the following memory location, and jump node 0 and decrement CX, and CX at that time will be 1, and we go back to back. Okay, then we're gonna add the 48, so we're gonna take the last result in AL and add to it 48. 48 is 0, 0, 1, 1, and 4 zeros. And here we also have no carry, so this result will go to AL, and remember, and AL, and we will not increase AH, so AH at the end will have this value here. So together AL and AH is basically the final result. So AX basically, which is the combination of AL and this is AH and AL, will have the final result, and we're gonna put this in sum at our final step here. Okay, guys, that's maybe one may say if we use AX from the beginning, we will not need the jump no carry over or incrementing AH. And that's absolutely right, but it's good to know such such maneuver, because you may have a situation in which you need more than 32-bit, and remember, the biggest, the largest or the biggest, register is EAX, 32-bit. So in case you need more than 32-bit, okay, then you have to do some kind of tricks like this. Okay. This is now the introduction of ADC. We said that add if carry. So this is another instruction exactly like add, but it will make the addition only if the carry is 1. So basically, you can replace these two lines with that line. Because in these two lines, we say, if there is no carry, go to over. If otherwise, we will increment H. So we can replace these two lines with the following: ADC AH00. So add 1 to AH if the carry is 1. ADC by itself means add 1 to H. That's why we put here 0. because the addition here by default will add 1 to each, but only if the carry is 1. Okay, and this is, for some reason, this is faster. Of course, you have reduced the code by 1 line, and for some reason, due to something called pipelining, this 1 line is faster than having a jump not carry over and increment h, or these 2 lines. Okay, now subtraction. Again, we're gonna do the subtraction here for the unsigned numbers. Okay, here is the general format for the subtraction operation. You have the mnemonic sub, then destination, and then source, exactly like the addition, although here it's a subtraction. So this is equivalent to saying destination equal to destination minus source. Okay, to do the subtraction on a paper, with a paper and a pen, or to imitate what the processor will do when you subtract 2 numbers, you should follow these 3 steps here. Okay, first, you will take the 2's complement of the source operand, this operand here, which will be negative, and we said that in our processor we don't do subtraction, we actually do addition. So in our subtraction we convert this source operand to its 2's complement. Okay, and we're gonna add. So we said in our first lectures, in our first and second week, we said that in subtraction we don't actually subtract, we add the 2's complement, and the addition of the 2's complement to the to some number is equivalent to making a subtraction. The important step here, which you might forget, that's why I put it in red here, is to invert the carry. So whatever, if the carry was 1, after this operation you invert it to 0. If the carry was 0, you invert it to 1. And based on the carry, after you invert it, if the carry is 0, then the result is positive. If the carry is 1, then the result is negative. And remember to invert the carry after you do the second step, after you do the addition. Then you make the judgment, over the number that you have based on the inverted carry. Good. So let's see an example here. So we're gonna subtract 3f minus 23. Remember, 3f as a number is greater than 23. How we know this? That's very simple. Just look at the the most significant digit. This is a 3, this is 2. It's like you compare, for example, 99 to 88. How we could know which is bigger than the other one? Just look at the most significant digit. This is 90, this is 80. So that means this one is greater than 88. Exactly here. So 3f is greater than 23. So let's do this subtraction. 3f is actually 0011, and the f is 4 ones. 23 is 0010, and the 3 is 0011. Okay, we said that we will not do the subtraction in that way. We will take the 2's complement of that guy, the second one, the 23. 2's complement is 0011, 1011. Then you add 1 here, so it will be 1011, 1011, and remember the first operand 0011, 1111. Then you do addition, normal addition, and remember to invert the carry after you finish. So 1 plus 1 is 0, and we have a 1 as a carry. 1 plus 1 is 0, and we have a 1 as a carry. 1 plus 1 plus 1 is 3. 3 is 1, 1. So you have 1, and you have 1 as a carry. 1 plus 1 plus 1 is again 3. So you have 1 and another 1 as a carry. 3 again, 2, 0, and we have 1. 1 plus 1 is 0, and we have 1. 1 plus 1 is 0, and we have 1. So there is a carry here. So the third step, and the most important, is to invert this carry. So the carry is 0. It's not 1. Then you judge about this number based on the carry that you have. The carry that we have now after the inversion is 0. So that number is positive. And that's expected because 3f is greater than 23. So that's the final result. So the final result here is that number in binary, or you can say it's 1, and this number is C, 1C. Okay. This is another example. Now we wanna, subtract 4C from 6C, or 6C from 4C. I'm sorry, it's the opposite. Now there is a problem here because 4C is less than 6C. So the result here would be a negative number. Okay. So let's do it. So 4C, 4 is 0, 1, 0, 0. C is 1, 1, 0. C is 12. And 6E, first 6 is 0, 1, 1, 0, and E is 1, 1, 1, 0. We're going to take the 2's complement of that guy. So you invert first. Then you add 1. So 1 plus 1 is 0, and we have 1. So that's the number. So we're gonna, add 0, 1, 0, 0, and 1, 1, 0, 0 to 0, 1, 0, 0, 1, 0, 0, 1. Let's do that. 0 plus 0 is 0. 0 plus 1 is 1. This is a 1. This is a 1. This is a 1. 0. This is 1 again, and this is 1. And there is no carry, right? But we invert this carry. So the carry will be 1. And after inversion, we judge on that number. So since it's a carry that we inverted is 1 now, this number is negative. And to know the actual result, we should take the 2's complement. So the 2's complement here is 1, 0, 0, 0, 0, 1, 0, 0, and you add 1. So this will be 0, 1, 0, 0, 0, 1, 0, 0. So this is the actual result. This is the actual. So the result here, which is a negative result, is minus. And this number is 2. And this is basically how much is 2? 22 hexadecimal. So that's the actual result. Okay. And if we look here at the program takes care of that inversion. So after making the subtraction, okay, we need to take the 2's complement of the output. If it's a negative number. So that's why here we check the carry. If the carry is 1, then we need the 2's complement. And here is how you do the 2's complement. So you first make the complement, then you increment by 1. So to take the 2's complement of any number, you invert it first, you invert each bit, then you add 1. So here we are saying, if there is no carry, go directly to here. And move the, the result into data 3, which will take the subtraction. But if it's, if the carry is 1, that means it's a negative number. So we need to take the 2's complement first. By incrementing here the destination, which has the final result, DH, and add 1 to it. Okay. The final, the final instruction or mnemonic here that we're going to discuss is what's called subtract with borrow. This is equivalent to ADC. Add if carry. Add if carry equal to 1. Okay, this is basically the same, or very, very equivalent, but the subtraction context. And it's usually used when you have a multi-word number, like this example here. So look at the the 2 numbers that you have. So these two numbers, word is 16 bits. So, and remember 16-bit, if you have, if you have a number 16-bit and you want to represent it as hexadecimal, this will be 4 digits. So remember, look at here. So this number is the first number here is AF26. This is 4 digit, fifth, sixth, seven digits, 7 digits, hexa. So that's for sure more than 16 bits, or need multi-word, more than one word to be represented. And that's why here we use the DD directive, which means define double word. So the following number is double word, and it needs really 2 words here. Again, the second number is B369214. So we have here how many digits? 1, 2, 3, 4, 5, 6, 7 digits again. So again, this needs 2 words. That's why we also use double word for data B variable. And we're gonna put the result in a variable called the result, which is also double word. Good. So to explain this, this example, we're gonna make a very big illustration here. So we're gonna first subtract the 2 numbers, the 7 digits number, which will be very big in binary. Then we're gonna see how subtract with borrow will save us, or will be used to do this subtraction. So let's do it. So the first number is 0110, 0010, 0101, then 0110, then 0010, 1111, and 1010. Okay, good. And I'm gonna divide them into like this. Four bits, so that we are not confused. So then the second number is 1101, 1100, then 0110, then 1001, then 0100, 130s, and 0010. And it will be long, and I'm gonna do the subtraction without the 2's complement. I'm gonna do direct subtraction, okay, which is of course equivalent. We just need to understand, the idea behind, sub SPP, or subtract with borrow. Okay. So let's do the subtraction here, the basic subtraction to understand the concept of borrow. So 0 minus 1, can't be done because 0 is less than 1. That's why we're gonna borrow that digit here from that digit, or from that bit. When you borrow something, this guy will be 2. You can write it as 01, or you can write it as 2. This is a paper and a pen, and this guy will be 0. So 2 minus 1 is 1. Then again, 0 minus 1, again cannot happen because 0 is less than 1. So we're gonna borrow. We can't borrow them from that guy because it's a 0. So that guy, the third bit, will borrow that 1. So this one will be 0. This will be 2. Then we're gonna borrow now. So this will be 1, and this guy will be 2. 2 minus 1 is 1. Remember now, the third bit becomes 1. So 1 minus 0 is 1. Then 0 minus 1 again can't be done. So we're gonna borrow that one here. This one will be 0. This guy will be 2. 2 minus 1 is 1. So the first digit will be F. Now the fifth bit, which is that one here, becomes 0. 0 minus 1 is can't be done. So we're gonna borrow 1. So this guy will be 0. This guy will be 2. 2 minus 1 is 1. Now 0 minus 1 again can't be done. So we're gonna borrow that guy. This guy will be 2. 2 minus 1 is 1. This becomes 0. 0 minus 0 is 0. 1 minus 0 is 1. And that's B. Then 0 minus 0 is 0. 1 minus 1 is 0. 0 minus 1 can't be done. So we cannot borrow from this digit, from that one, or from that one. So we're gonna borrow this guy. So this guy will be 0. This guy will be 1 because we're gonna borrow here 1. So it will be 1 again because this one will again borrow. So this will be 2. 2 minus 1 is 1. This become 1. 1 minus 0 is 1. That's C. 1 minus 1 is 1. I'm sorry, 0. And 0 minus 0 is 0. 1 minus 0 is 1. And then we're gonna borrow. This will be 0. This will be 2. 2 minus 1 is 1. This is again C. Then 0 minus 0 is 0. 0 minus 1 can't be, done. So we're gonna borrow that guy. This guy will be 0, and this guy will be 2. 2 minus 1 is 1. 0 minus 0 is 0. 0 minus 0 is 0. And so this will be 2. 0 minus 1 can't be done. So we're gonna borrow that guy. This guy will be 2. 2 minus 1 is 1. Then 0 minus 0 is 0. 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 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 0 is 0. So this is basically 1. This is basically 2. So this is the final answer. This is the final answer. And it's positive because the second digit, this guy, is less than that guy. Okay. Now this is how this is done, with a complete, number of bits. Although in our, registers, we have 16 bits, 8 bits, 32 bits. So what's gonna happen if we use 16 bits? So for some architecture in x86 processor, there were no 32 bits. So we have to use the 16 bits or one word. So we can't do this subtraction, as a whole at one time. And we must divide our operation into multiple operations. Because if you have 16-bit and you don't have 32-bit, registers, you must divide this. If you have 32, that's okay. But if you have only 16, then you must divide your operation into multiple operations, and that's the rule of subtract with borrow. So what we're gonna do, just look at here. So we're gonna divide it into two words. This is one word. This is one word. This is the second word. Okay. So we're gonna do this first word first, subtraction first. Then if we have a carry, that means that number was less than this number. The first number, is less than the second number, and we need to borrow. Basically, that's the meaning of borrow from the second operation. So we're gonna do. Let's do it. So we're gonna do the first operation first. So 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 0. And we're going to subtract from 1, 1, 0, 1, 1, 1, 0, 0. Then 0, 1, 1, 0, 1, 0, 0, 1. So you are free with a paper and a pen to do it, you know, as direct subtraction, or to take the 2's complement and then make addition and invert the carry, whatever you like. This both operations will give you the same answer. I'm gonna do the direct subtraction. Okay, 0 minus 1. Remember, this number here, this number is less than this number. So the first number, let's talk it number 1, and this is number 2. Number 1 is less than number 2. So the result should be negative. Or we're gonna say there will be an extra borrow that we should do. Borrow, not carry. So that also we're gonna use the same bit, the carry bit, but you know, it's a borrow now, not a carry, because the operation is different. It's a subtraction operation, not addition operation. So let's do it. And we are expecting that the result will be a negative. So 0 minus 1 can't happen. So we're gonna borrow that guy. This guy will be 0, and this guy will be 2. 2 minus 1 is 1. 0 minus 1 again can't happen. We can't borrow from that guy, the third bit. So we can borrow from that guy. This will be 0. This one will be 1, and this guy will be 2. 2 minus 1 is 1. 1 minus 0 is 1. 0 minus 1 can't happen. So we're gonna borrow that guy. That guy will be 2. 2 minus 1 is 1. Again, F. And you must have the same result, as we will see. We get the F already. 0 minus 1 can't happen, so we're going to borrow that guy. This guy will be 0, this guy will be 2. 2 minus 1 is 1. 0 minus 1 can't happen, so we're going to borrow that guy. That guy will be 2. 2 minus 1 is 1. 0 minus 0 is 0. 1 minus 0 is 1. This is B. Again, we're going to get, we must get the same for basic first 4 digits. 0 minus 0 is 0. 1 minus 1 is 0. 0 minus 1 can't happen. So we're gonna borrow that guy there. You know, so this is the closest one for us. This will be 1. This will be 1. This will be 2. 2 minus 1 is 1. 1 minus 1 is 1. I'm sorry, 1 minus 0 is 1. This is C. We get that guy. 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 1 is 1. Oh, I'm sorry, 1 minus 0 is 1. And then 0 minus 1 can't happen, but we don't have, a number here to take from or to borrow from. So what's gonna happen here is the carry will be 1, and this will be 2. 2 minus 1 is 1. This is C again. So after this operation with the first word, the carry will be 1. If you do it in the same way that we explained before, taking the 2's complement of the second operand, okay, you're gonna see that the carry is 0, then you invert it to, and it will be 1. So you're gonna have the same, same result. So now when we do the second word, we should add, one extra step. So here is the second word from each number. Which is subtracting 1. Which is what? Which is subtracting 1, which is basically borrowing that 1. If we do the complete, complete subtraction with the whole numbers, subtracting this 1 means we take a borrow. We take this 1 as a borrow, and that's what happened. Look here, it's a 0. That's what we're gonna do now. So 1 minus 0 is 1, and then 1 minus 1 is 0. 0 minus 1 can't happen, so we're gonna borrow that guy. That guy will be 2. 2 minus 1 is 1. 0 minus 0 is 0. 0 minus 0 is 0. This is 2. 0 minus 1 can't happen, so we're gonna borrow that guy. This guy will be 2. 2 minus 1 is 1. Then 0, 0, 0. This is 1. Then 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 0 is 0. This is 2. This is the last. That's basically the idea behind, you know, the use of subtract with borrow. Let's check the code now. Here is the code. Okay. So since we're gonna he's using, you know, 16-bit register. Okay, because again, some architectures doesn't have 32-bit registers. Okay, like x86, for example. Now we have 32-bit, you know, in our Visual Studio. If you're gonna use ECX or AX, it's a 32-bit register, and you can do that operation in one step. But if you don't have, if you have a bigger number, more than 32-bit, then you must use a subtract with borrow. So here we move first the first word, and here is how you do it. Remember, this guy is 16-bit to one word, but this number here is more than one word. So you must use word pointer. This is a directive, word pointer directive, that tells the assembler, hey assembler, please bring me what's equivalent to AX. AX is 16-bit, one word, so it will bring only the first word of that number, which is 6F2, I'm sorry, AF26. Then we subtract from 6 to FA, we subtract this guy, 963B, in that the second step. And then we move the result, you know, of which is in AX now into result. After that, we do the, you know, the next subtraction. Okay, and here we're gonna use subtract with borrow, because if there is a borrow, that result or a carry basically, but you know, in that context it's a borrow, not a carry, because it's subtraction. If there is a borrow from the first operation, the first subtraction, then we need to make an extra -1, which is that step here, you know, when we do the subtraction. And that's why we use subtract with borrow. If the borrow is 0, subtraction with borrow will be exactly like subtraction. So if the carry or the borrow basically was 0, subtraction with borrow will be just exactly as sub. Okay. Then finally we add the result into, you know, the result, but we shift by 2 because, you know, the original result, the first result has 2 bytes or 1 word, and this is another word, so we must be shifted, you know, to a higher location in the memory. So if this is the memory, for example, the first result will take 2 bytes like this. So here is the first byte of the result variable. So we must point to the, you know, to a higher value, so to store the next, you know, the next result. Okay, guys, that was it for the, you know, the addition and subtraction, you know, instructions. Thank you for watching, and see you in the next video. Bye-bye.